Begin with. Thanks. So first of all, I'd like to thank the organizers for this great opportunity to introduce our recent attempts towards the Bayesian constraints on nuclear structure via isobar collisions. So, oops. Oh, you need to
I think the box focus is changing right now.
Okay, thanks. So to begin, I would like to talk a bit about the history that initially the isobar program was designed to detect the current magnetic effect in heavy ion collisions. So the expectation before the isobar collision was that if there is CME, then we expect the CME correlator would be greater in ruthenium system compared to zirconium system because there are more protons in ruthenium and the magnetic field is stronger. Whereas if there is no CME, the expectation is that the background of these two systems could be very similar. So if we measure that the CME correlators in ruthenium to be consistent with zirconium, we will be able to say, okay, the CME is too weak to be detected, and we could at least set an upper bound for the current magnetic effect. And after reviewing the results, we know that what has been measured tells us the CME observable, CME correlator, is smaller in ruthenium compared to zirconium. So it was a bit surprising, but immediately every people know the answer. So, one thing I would like to, emphasize to the whole community is the conclusion of this experiment tells us. Let me use the mouse here. Tells us no CME signature that satisfies the predefined criteria has been observed. This is not an equal mark to no CME. We cannot simply strike out the rest of this sentence. So the reason is our expectation that the non-CME background for ruthenium and zirconium to be identical turns out to be incorrect. Because, reported by the same paper, we know that the bulk properties, the multiplicity and the elliptic flow turn out to be not identical in these two systems. So we are expecting non-identical background in these two systems.
It's the ratio in the lower left plot.
So the ratio is
the error bars. Are they? Does it have correct error bars, or is this non-monotonicity just the fluctuation?
Well, this is, I would say, because of the centrality cut. Because in this
one cut to make.
I'll say something in the next talk.
Okay. So this way for 30 minutes.
It's a question to clarify. So the open point and the closed point and the upper panels, they are actually on the same centrality.
They are on the same centrality. They are just shifted horizontally for better reason.
Okay.
So yeah.
How do you know it's not your centrality determination?
Well, maybe if Petrich was here, he may urgent to answer.
In the next talk, I have lots of slides.
Don't take less centrality literally. It's multiplicity cuts.
Yeah, I know.
And then you interpret it, and you call it centrality. You don't have.
Yeah. But the composition of matter is different, so the produced particles will be different.
That's right.
To some degree.
That's exactly right. So, well, because this is the star result. For my personal point of view, better way to compare these two systems is not to compare them according to identical centrality region, but to identical multiplicity region. That would further suppress the difference in the background. So, I mean,
Do you have
for,
a figure that shows that?
pardon?
Do you have a figure that shows that?
My collaborator, my former supervisor, Jun Feng Liao, would talk about this on Wednesday.
Okay.
Yeah, he will talk about this. So for, CNE physics, this causes lots of headache, I would say, because this requires a careful with analysis of the situation without CNE background. So again, Jin Feng will talk about this this Wednesday, and also one could refer to Fu Xiang's talk last week. So both of these contain a lot of information about how one should, reanalyze the baseline without CME. Okay, this is a headache for CME, but for other physics, this is a new opportunity. So it has been proposed by, our organizer, Giuliano, Zhang Yong, and Chun Jian, that the difference in these two systems is a great opportunity to explore the difference in the structure. So if we look at the ratio of multiplicity distribution of elliptic and triangular flow, as well as the variance of the transverse of the radial flow, we can see the ratio of these two systems are significantly different from one. And we already know that these observables in heavy-ion collision, they are very sensitive to the transport details of the quantum plasma. If you change the viscosity, or if you change some other parameter, you might expect the V2 or V3, they are visibly different. However, if it's possible to make high statistics experimental results for these ratios in an isobar collision, these ratios, they are expected to be insensitive to the transport details, so that if we only look into the ratios, then it might be a clear way to reconstruct the nuclear structure that is independent, or at least insensitive to the transport properties. Then at this point, I was very excited, but I asked myself a question. For a single system, it is clear that one can reconstruct, everything out of a Bayesian analysis. One can reconstruct the properties of the initial condition. One can reconstruct the transport properties of quantum plasma. However, if in this isobar systems, if we only look at the ratio of these two systems, is it possible to simultaneously recover the nuclear structures of both the systems only from the ratio? So this kind of motivates our, I will call it a proof of concept study, trying to reconstruct the nuclear structures of both nuclei simultaneously from the observables, and or only their ratios. So this is basically, I have covered the background of the talk, and by reconstruction, there is always meaning of reconstruction, because we are not possible to, ideally recover the say nuclear structure parameters that is identical to the truth. There is always some probabilistic description. So we are going to apply the Bayesian inference in order to sort of reconstruct the likely distribution of the structure parameters. And we are going to show our results for this proof of concept study. And finally, I'll summarize an outlook. So I will talk a bit about the Bayesian analysis. The underlying idea is the Bayes theorem. If we would like to, well, the Bayesian theorem tells us the likelihood of distribution of the parameters of some model given some experimental data or observed data, it equals to the probability distribution of the data given parameter that multiplies the prior knowledge of the parameters. And I mean, they could be different by a normalization constant. So that's why I put a proportional mark here. So in this topic, the parameters or the model is the nucleus structure, whereas the data is the data that can be observed in heavy ion collisions. And therefore, the likelihood is that, yes.
Can you tell me why you interchange the names? Usually the probability of data given the parameters is called the likelihood function. And the thing on the left-hand side is called the posterior distribution for the parameters. Why did you interchange these?
So probability of the data is that, okay, if we compute
I'm just talking about a convention. This is usually called the likelihood function.
Yeah, I will call
wondering about your choice of letters.
Yeah, well, I will call if there is no prior, and the left-hand side would be the likelihood of the parameter, given this fact.
If you have no prior, then the posterior is proportional to the likelihood.
Right.
It would have written it in the opposite way.
Okay. Thanks. So, L here is the distribution of the nucleus structure parameter. Whereas P is, suppose we have fixed some model parameter and compute observables, and we compare this observables to what has been measured in experiment, and this tells us the probability of the experimental data that satisfies the model calculation, and it is quantified by this exponential of -12 chi-square. So this tells us one needs to find a model to map the nucleus structure to the final state observables. So for those who are not familiar with heavy ion collision, I would say the state-of-the-art model is summarized by Schun's plot. One can start from the nucleus structure and sample the nucleons out of it, and then there is some initial state model that tells us the event by event fluctuate and initial configurations. With this, one can solve the hydrodynamic equations and freeze out, and finally simulate the scattering between hadron gases and hadron gas, and eventually measure the observable that can be detected in experiment. So it sounds like a very sophisticated framework, and it is. It takes a lot of computational powers to run such a simulation. So before spending a lot of computational power for this Bayesian analysis, we would like to perform a proof of concept study first. So the idea of this is that from hydrodynamic knowledge, we know that there are very good correspondence of the initial state property and the final state properties. The properties that can be observed in the final state, in the experiment. We know that if a system has more initial energy, then we will expect more final state charged particles. So there is strong correlation between the initial energy and the multiplicity. And similarly, if we measure the second or third order anisotropy of the initial state, they can nicely correlate with the final state second and third order anisotropy of the in the momentum space. And finally, if we measure the density, the energy density of the initial state, it is nicely correlated with the transverse momentum of the final state, the radial flow. So in this proof of concept study, we make a yes.
When you say initial, it means the calculation or in the,
when I say initial, I mean the profile that is generated right after the collision. So this is the initial, and final is the
so you can only have those quantities in your calculation, right? You can't. Yes. Or you can say that whatever you measure when you say final reflect the initial.
sorry, could you repeat your question?
Okay, now I'm confused about the relationship between your initial and the final in terms of what is theory, what is calculation, what is the what is the measurement?
Both. In theory or phenomenological simulation, one can generate the initial state from some model, and after this, stage, one can also solve the viscous hydrodynamic equations. This can be done, in theoretical calculation, and finally, for this Hadron gas phase, which means the system has been hadronized, and the degree of freedom represented by a bunch of hadron particles, and people can, in simulation, people can simulate the scattering between them, and in simulation, people can get this, but it will take a lot of time. So in this study, we are not going to do so.
Can you say what is D-perp?
D-perp is the energy density. So
how is that different from the energy divided by the volume?
Exactly. It's the total energy divided by the transverse area.
So that means N charge and PT are proportional to each other because both are predicted by the same volume.
N charge and
Same.
no, because if you have a system with the same amount of energy, but the transverse area is different.
They're related, but they're not proportional.
Right.
All the question is related.
So in this proof of concept study, we take a kind of a bold assumption that we assume one can use the Monte Carlo Glauber model. We could assume it to be a perfect estimator to map the initial state to the final state. So basically, we run Monte Carlo Glauber simulations, and we extract the information of this initial state quantities, and we assume that the final state observables, they can be computed directly through this one-to-one mapping rather than correlation. So we assume that final state multiplicity, charge multiplicity, is proportional to the initial energy, and similar for the anisotropies. Whereas, as Jiang just mentioned, the radial flow is some monotonic function of the energy density. Yes.
My talk, I'll say, show you a little bit with this lambda 2. I think it's important. It's a little bit different for ruthenium and zirconium, and that's important. I'll say something.
Okay, cool. So, I mean, again, this is bold assumption that is not realistic. But the idea behind this is, as a proof of concept study, we would like to, know an answer of yes or no, rather than a very precise reconstruction of the parameters. So, out of this, proof of concept study, what we would like to learn is whether or not we can reconstruct the model parameters out of the the observables that is desired.
Can I ask a question?
Yes.
So lambda 2, lambda 3 have inverse energy. Is there units?
Here.
Right. Yeah.
That's just the proportionality
That's not
constants.
energy, that's the eccentricity.
Oh, eccentricity.
Yeah. So epsilon 2 is the spatial eccentricity.
Okay.
Yeah. So we start from, say, some models for the nuclear structure. We run, a lot of MC-Glauber events. We take this assumption. We then we fill the histograms of different events according to, the multiplicity, and we generate our quote-unquote observables. So the goal is to reconstruct the nuclear structure. So by this, we take the parameterization of the width section distribution, and what is really to be reconstructed, the radius, the diffusiveness, and second order and third order deformation coefficients. And again, because this is a simple model, and our experiment that's to be compared are not real experiment data. We try to use the MC-Glauber with some fixed with some known parameters to provide our experiments. So in the technical language of Bayesian analysis, this is equivalent to a mock test.
Closure test.
So suppose we have infinite computational power, we can scan the whole parameter space. And for each parameter set of RA beta 2 beta 3, we can compute observables and compute the chi-square, which is the difference between the observable and the desired observable. And with this, we know that the posterior, because we have assumed flat distribution as prior, we know the posterior distribution of this parameter set. But in realistic, we don't have infinite power, computational power. So we have to do an emulator, which starts from a given number of simulations that really tells us this information, and do the either interpolation or parameterizing fit to get the chi-square dependence of these parameters. And then we need to run the Markov chain Monte Carlo, which is basically some random walk in the parameter space. So in the parameter space of this RA beta 2 beta 3 parameters, we take iteration of random walks, and the probability of keeping the next iteration is based on the ratio of this posterior distribution. So after sufficient amount of these random walks, we were able to HDMI. Oh, the fact is
It's over here.
So after sufficient amount of random walks, we were able to construct an ensemble of parameter sets that satisfy this likelihood distribution.
That is not full.
Did you take it out of full screen?
Yeah.
And do it to the full screen.
Yes. So to begin, we start from real mock tests based on single systems. So we start from a known set of parameters, run high statistics MC-Glover simulations, and assume that to be our experimental data. And we try to run MC and reconstruct the model parameters, the structure parameters out of this mock data. And this is what we get. So the known parameter set, the ground truth, are represented by this red dots and lines. And you can see that they agree, the reconstructed value is consistent with this ground truth. So this is a test of our
true booklet read.
it is, well, I would say within 2 sigma, because there is always statistical fluctuations. So, to me, I'm not surprised to see this.
Are these bars your prior?
Pardon?
Are the hash marks your prior?
Well, the prior is much wider than what's shown here, and we assume a uniform prior.
This is just one event, right? It's a multiple event or the best.
This is one parameter set, not.
Yeah, exactly. That's
Yeah.
what I mean. One parameter set.
That's
So
right.
what about the others? That you show relatively good. What about?
Mhm.
You need some statistics to really.
This is not one event, but we start from one parameter set and run a lot of simulation events.
Yes.
And this is for lots of simulation events. And for another parameter
Not
set,
only is beta phi, right? If you look at the speech set, if you look at the A beta phi correlation, this dot is white. So if it's white, it's 0 probability. And if it's real data, you would kind of think, okay, there are all kinds of effects, but this is a closure test. So the model has to, this has to be statistically completely sound, right?
Yeah.
If you do everything correctly, it would be not an impossible play.
I think
And you didn't mention, but in this chi-squared formula, there's this sigma AB, which is the correlation matrix.
right?
And well, I read the paper, but that wasn't clear for me, like in the epsilon 2, how many centrality classes, for instance, you take. These points are correlated. And if you don't take these correlations into account, and you didn't, then you kind of have like 10 data points, which are all correlated. And then you kind of get much narrower distributions.
I agree with you on the correlation part. So we are running new tests on that. We will update our result according to that.
what this test showed you is that in your model, there's no ambiguity, right? You have a one-to-one correlation between your input and your output, but if it turned out that it depended like that on the square at the two eccentricities, one squared plus the other squared, then square root, and somehow you found out that you have no sensitivity to independent values of the eccentricities, then you would see it doesn't work. But other than that, doesn't tell you that your connection between the eccentricity and final results are correct, right?
I agree with you. The whole work would not answer that question. That question need to be answered by running realistic simulation.
Well, my question will be your beta 3, right? So you show 2 parameter set, the first one and this one. Both of them show that they are on the outer edge, 2 sigma away.
No, to
But-
show the next example that you have.
By the way, we only have 2 minutes left, so
Oh,
I would say that maybe let's let Suji finish real quick and then we can discuss more.
Yeah, so we did for ruthenium and the same for zirconium. And the next question is, well, we can do some reasonable job for the single system. But how about for both systems? If I only focus on the ratios, can I reconstruct the parameters? So here, I apologize for a little bit busy plot, but shows the learning histories of every Markov chains. So here, from left to right, correspond to the different parameters in ruthenium and zirconium. And in the lower panel, it shows the trajectory, the position of each Markov chain. So each Markov chain is represented by a different color. And in the upper panel is the histogram of these chains. So first of all, we can see that these chains, they are well separated from each other. And also the histograms are separated from each other. So this tells me if I start from, this particular point of the parameter space, I'm going to get a histogram of, like this. Whereas if I start from a different point in the parameter space, I'm going to get a different histogram. So this tells us if we only look into these ratios of observables, we are going to find.
Yeah, you can wrap up and then.
We are going to find no unique solution. Only ratios does not tell us simultaneously the nuclear structures of the isobar system. However, if we look into not only the ratios, but for the multiplicity distribution, we look into the multiplicity of both systems. Then we are going to find that different Markov chains, they agree well with each other, and the histogram, they overlap nicely with each other. So one thing that I would like to emphasize here is that the multiplicity distribution, they are supposed to be insensitive to the transport details, so that even if we could allow ourselves to reconstruct the nuclear parameters according to this set of observables, we would be able to reconstruct the nuclear structure in a way that is insensitive to the transport details.
Are you only using the shape of the multiplicity distribution, or are you using the actual value? Because the actual value depends on the content, right? It's only the shape that obviously comes to.
In this study, we have to depend on the the absolute value. It's a good question that whether we can allow let's say a rescaling factor for the multiplicity distribution. I think we could look into this at some point. So I'm going to skip this, and basically the most important summary of this work is if we only look at the ratio of the observables, we cannot reconstruct the nuclear structures without any prior knowledge. However, if we look into the multiplicity distribution with ratios of others, then we shall be able to do so. And of course, this is only based on a unrealistic assumption. Model for initial and final mapping, but we are running more realistic calculations for that.
Was actually. Yeah.
Could you explain some more why the multiplicity distribution give you the power to convert to single solution?
Because the multiplicity distribution on its own, it captures a lot of the information about not only radius and stiffness, the diffusiveness, but also, let's say for ultra central collisions, it is sensitive to the beta 2, beta 3 deformation. So if we have good information of how the multiplicity fluctuates, especially the tail, then we shall be able to know much more about the nuclear structure.
Yeah, I want to make a comment about one of your assumptions related to one of your conclusion here, saying that even the ratio, okay, the ratio is not sensitive to the detail in transport models. I think that your assumption. Okay, even if you see some difference, that you can't uniquely relate that to the nuclear structure. It could be due to the isospin effect. You see, for people working at low energy, we try to learn about this the signature energy or the isospin independence of the nuclear cross-section itself. We use the ratio to get rid of all the isoscalar effects. Okay, then you can isolate out the isovector effects. So the assumption that the ratio is independent of detailed transport models has to be kind of conditionally correct. Maybe depend on the energy. At high energy might be true, but when you go to low energy or go to peripheral reactions, when the interaction between spectator and participant, in that region you may have some kind of isospin diffusion due to mean field and so on. So if you see some dependence, it doesn't necessarily imply a nuclear structure effect. Could be some dynamical isospin effects, during the reaction. That's my comment.
Thank you for the comment. So as far as I can tell the observables, we are looking into, say, the multiplicity, the anisotropy, they are not sensitive to the isospin effect. So
It's too high in energy.
Yeah, they would just pass through each other, so you don't have any baryon stopping, so it just essentially is someone who wants initially.
Yeah, I have a high energy.
So, Uli has a question, then I'll go. Oh, Zidu was first, okay, so, Zidu, can you, is he on mute?
Yeah, you can unmute. Can you unmute? There you go.
Hello.
Yeah.
Okay, great. So yeah, I have a question. So first, thank you, Shujo, for your very interesting talk. So could you please go back to your expression of that density, that Wood-Saxon density expression? Yeah, I have a very simple question on that Wood-Saxon density. So is that the nucleon density, or is that the proton density, or is that the neutron density?
So this is assumed to be the nucleon density. In high energy collisions, we don't distinguish between proton and neutron.
Okay. So my next question is that among these 4 parameters, are those 4 parameters somehow equally sensitive to your observational data, or which parameter is most sensitive to your data, and which one is the most difficult one to be reconstructed?
It really depends on what observables we are talking about. So for instance, for V2 and V3, especially for ultracentric collisions, they are respectively sensitive to epsilon 2 and epsilon 3.
So beta 2
Beta
and beta 3.
But yeah.
You're trying to say.
Sorry, beta 2 and beta 3.
So it's that, I come back to the same question again, is this that how many parameters set where you look at the predicted whatever observable beta or whatever, and the true one? Because you just show a 3 parameter set.
Yeah.
Do you have 50 or do you have
We have 200, and we learn our control emulator, say basically a parameter fit according to that 200 parameter set. And because it is fitted, so they are supposed to describe, the emulator are supposed to describe the simulation data, and they do.
Yeah, so why don't you just plot the true versus predicted? Then you can see the, then one can see the correlations.
Let's leave this real quick.
Nobody else?
Uli, do you have a quick question?
Yeah, I mean, I'm worried about your closure system, two sigma deviation. You can probably check into that more in detail by improving the statistical precision with which you generate your initial eccentricities.
Yeah,
And see how, you have to figure out if that's an emulator error or whether that, but the way it stands, I don't think you will be able to use that for any serious parameter estimation.
The correlations are nothing, so you don't expect.
So let's leave this as a comment, otherwise we're gonna get late in those things, Shuji, one more time.